All right, let's get started. Before I begin, we have a representative from the Society for Women Engineers to have an announcement.
So, Society of Women Engineers is putting on an internship panel. We'll read a little bit about it right there. So the panel will be current students who have had internships at various companies. So it's never too early to start thinking about getting an internship. So you can go there, ask them questions on how they got the internship, what it was like, what they didn't like about it. There will also be food there. We're trying to get a variety of pasta bakes. There will be a vegan and a gluten-free option if you need that. So it's next Thursday at 5:30. If you have any questions, you can email uofuswepdc@gmail.com. Any questions you might have right now that I can answer? Yes?
Is this for CS majors or is it for all STEM?
It's for everybody. There will be a CS person there on the panel. So yeah, and men and women can come to this. Did that answer your question? Okay. Nope. All right. All right. Thank you.
Okay, so PS8 is due tomorrow or Friday if you take a late day. PS9 will come out tomorrow, hopefully, not Friday. And PS9 will involve recursion, the stuff we've been talking about this week. Any questions or problems about anything I could help you with before we start? And one piece of advice, before you attempt to implement the big rat class, be sure you understand the rat class. Okay? That seems like an obvious thing to say, but you know, if you don't understand at all how the rat class works, you're not going to make the big rat class work. On the other hand, if you do understand the rat class, big rat should be easy. Okay, last time we were talking about the pedigree, the thing you looked at lab yesterday. And let's talk about what you did at lab yesterday. So if you have a pedigree tree, remember there are two kinds. What are the two kinds of pedigrees? Yes? Okay, so he said an empty pedigree, which we're representing with null, and a non-empty pedigree, which consists of information about a person, name, birth year, and a reference to two other pedigree trees, one for mother, one for father, either of which could be null or, in turn, another pedigree object. So when you're thinking about a big pedigree tree, don't think about it that way. Think about it as one of these two things. There are always two possibilities, either a pedigree object or null. So, given that way of thinking about things, if you want to make a string that contains all the names of everyone in the tree, and you want to figure out how to do it, you just got to think, what would I do for each kind of pedigree? And there are only two kinds. So what should you do if the pedigree tree is null? There is no information. What should the string that contains all the names in that tree contain? What should it be? Yeah? An empty string. So that's half your program right there. If the pedigree tree is null, you return an empty string. On the other hand, you may get a pedigree tree that consists of information about a person, in particular his name, and then two pedigree trees. So how do you compose a string that contains all the names of all the people that you can reach from the root? Yes?
Get the names of the people or the person in that pedigree, and then names of everybody in the father pedigree and everyone in the mother pedigree.
Okay. So you get the names of, you get a string that contains the names of everyone in the father tree by making a recursive call. Same thing for the mother, you get a string for it, and then you append that string together with the other string together with the name of the person at the root. So all these methods end up looking pretty much the same. So we'll copy the pattern here. Paste it in, and we decided if the pedigree was null, we'll just return the empty string. Otherwise, we've got to do something. We've got to recursively get all the names. That's not right. All the names from the father tree. All the names from the mother side. Okay, so those are those two recursive calls, one to get the father names, one to get the mother names, and then we decided we'd append them together. So we'll do that plus p dot get name. And there you go. Yes?
Do we have to use recursion for PS8?
Do you have to use recursion for PS8? No.
Would it be helpful if...
I can't think of any reason why it'd be helpful, particularly helpful for what you're doing. Okay? So these methods just, you know, once you get the hang of it, once you realize that these methods that work on these trees, that the structure of the methods is just a reflection of the structure of the trees. You know, there are two kinds of trees, so there's an if-else. And in one of the kind of trees, you've got to typically recursively solve the problem for the father and for the mother before recombining to obtain an overall solution. Once you realize that, these things get pretty straightforward. But until you realize that, they look very mysterious. So any questions I can answer about this? Yeah? Okay, so the question was, in a recursive method, do you always need a base case for it to stop? And the answer is yes. If all you have is a recursive call, then, and there's no way to get out of the method without making a recursive call. You've got infinite recursion. Any other questions? Now, I'll just make an observation at this point. We're using, what we have are pedigree trees. There's a particular kind of tree, but a more generic name for the kind of tree we're looking at is a binary tree. Or a binary tree, there's two branches from a given node, so mother and father in this case. And if you take 2420, you'll be spending a fair amount of time studying binary trees. It's a form of binary tree that makes tree maps and tree sets work in Java. You know, if you looked inside one of those tree maps or tree sets, you'd find a particular kind of binary tree. So this sort of recursive thinking and binary tree will carry over directly to 2420. What about to find out if someone has a birth year? Someone has a particular birth year. So you're given a pedigree and you want to know, is anyone in here born in that year? Okay? It's same thing, same pattern. Okay? If someone hands you a null tree and says, does anyone in that tree have this birth year? What do you say? Yeah, you say false. There are no people, therefore no birth years. Otherwise, well, we've got to call has birth year on get father. And on the mother. And we'll get back true or false. How do we combine those answers to obtain an overall answer? What's that? Okay. do wrong here? Oh, forgot the year parameter. Okay, is this correct?
For this case, yes.
Yeah?
You can see if the person that you first pass in has that birth year or not.
Correct. We need to look at the actual person's birth year. So P dot get birth year. And if that's equal to the year, or if the father tree contains someone with that year, or if the mother tree contains a person with that year, then we return true. Now, I had you read something about short circuit evaluation in the Zai book recently, maybe even today, I don't remember. And this is an example of it. What will happen if, let's say, we're evaluating a tree and the person at the root has the birth year we're looking for? Will these recursive calls happen? They won't. And the reason they won't is, as soon as Java sees that this is true, there's no point in looking at the rest of this, because nothing we could find out down there is going to change our mind. Even if they're both false, we're still going to return true. So if we're doing ORs, once we find something that's true, we're done. We can skip. That's called short circuit evaluation. And with AND, it's a little bit different. It's when you find something that's false, then you don't need to look at the rest of the conjunction. You can just return false right away. Yeah?
So here we have p.get birth year equals year.
Mm-hmm.
Would it be wrong to use has birth year and pass in p and the year?
Okay. So he's suggesting instead of this that we replace it with what do you think of that? In the back. Right. So assuming P isn't null, what's going to happen is, first thing we're going to do is call has birth year with the exact same P and the exact same year, which will immediately make that call again. We've set up an infinite recursion. And the reason this is an infinite recursion, well, you tell me, why is that an infinite recursion? These other two don't cause infinite recursions. Yeah? Say a little louder. Well, it's not doesn't really necessarily have to do with short circuiting. Yeah?
Because the same values are passed into the method.
Okay, because it's the exact same parameters that came into has birth year are being passed again. So nothing changes. With these other ones, what's changing? What's getting smaller? Typically, you want to see each time you make a recursive call, something gets smaller or closer to 0 or closer to infinity or something. Yeah? Okay, the bottom two have the same year parameter, but different pedigree trees, smaller pedigree trees. And as long as the tree is not infinite, you will eventually hit the bottom. So if we were to run this, so what do I have here? I have a main method, I think. All right, so let's see what happens when we run it. Okay, we got that infinite recursion with it has birth year. So up at the top, there'll be lots of these. But it was doing just fine until it hit that. So if we change it back, and rerun the main method, then it works okay. So you have to be careful. Any other questions about this? Yeah?
So in the if statement, would it be wrong to put if year is greater than p.get birth year? Would that also work instead of just p equals null?
Okay, so he's suggesting maybe if the year happens to be larger than the birth year of the root, that we could just return false right away under the assumption that we're not going to find anyone any younger, deeper in the tree. And yeah, that would work as long as you trust that that it really is a pedigree tree, right? It doesn't have any monkey business with years. Any other questions? Okay, now, on the one problem that you'll have on the upcoming assignment on PS9 is going to be doing something very similar to this pedigree tree, but instead of pedigree trees, what you'll be working with are mobiles. So if you think what a mobile is, it's sticks with strings and weights hanging from the sticks. So in what sense is that a binary tree? Yeah?
You could have mobiles hanging from your mobiles.
Right. You said you can have mobiles hanging from your mobile. So the simplest mobile is just a weight hanging from a string. That's a boring one. That's one kind of mobile. The other kind is a stick that's suspended from above and that has two simpler mobiles hanging from it. And you can imagine all kinds of questions you might ask about a mobile, like is it balanced? Is every stick level? What's the total weight of all the bobs, all the weights in the mobile, and so forth. So it'll be similar to this sort of thing. Just a different kind of binary tree. Yeah?
Are trees with non-true branches commonly used, like a tree with 3 or 4 branches?
Okay, so he's asking, I keep saying binary tree, 2 branches at most. Do you commonly see trees with more branches? Yes, you do. It's most common in computer science to see binary trees. But think about if you had to think about this problem. What if instead of wanting to represent a person and all of their ancestors, you wanted to represent a person and all their descendants? So not a pedigree tree, what's it called? Descendant tree?
Yeah.
A descendant tree. So how many branches would there be from each person? Depends how many children they have, which of course varies. Okay, anything else? Oh, one thing I meant to say to people viewing this live is we want to experiment with letting you ask questions. So Stefan is sitting there with his phone, and if you post a question to the comment, you can post a comment to the video if you're watching it live. Hopefully he'll notice and relay the question to me if there's not too much lag. Any questions?
Not yet.
Not yet, okay. Let's move on to another example. Okay, this example is really close to my heart because this was an assignment in my first programming class. And it's the assignment where I figured out recursion. I can remember sitting in a computer room working on this and suddenly realizing how to do it. And years later, I can remember the feeling I had. I was so excited that I had this breakthrough on the problem. So here's the deal. It's called Ponds and Islands. And actually, before we look at this, I want to show you something else. Okay, this is Google Earth, and we're zoomed in, and you can see that yellow marker. So what you're looking at is this brown area is an island inside this green area. So the water looks green here. So this is an island inside of a pond. Okay? If we zoom out, we see that that island that contains the pond is on an island in a bigger pond. So it's an island in a pond, on an island in a pond, on an island, which happens to be in northern Canada. That's apparently, people believe that's the largest such island in the world. It's about the size of a football field. The largest island in a pond, on an island, in a pond, on an island. And they don't think anyone's ever been there. It was found just by people that had nothing better to do than zoom in on Google Earth looking for things like this. But I couldn't resist showing you because we're talking about ponds and islands. Anyway. So here's how we're going to do ponds and islands. We're going to take files that contain hyphens in, this is the wrong place, hyphens and pound signs. So you think of the hyphens as being water and the pound signs as being land. And another rule we're going to have is we're going to require that the perimeter has to be water. And so the goal is to identify all the islands, basically count the islands, number the islands. And the way we'll do that is, in this one you see there are 5 islands. We've got this clump here, the big one, 2 small islands, and this guy here. So what the program will do is read in this information and write out that. So what it's done is identified the islands with letters. So all the first island it found is labeled with A. All the land is labeled with A. And with B, and with C, and with D, and with E. Okay? That's the kind of output we want to see. And it's, of course, possible for the islands to contain ponds, and the ponds can contain islands. So here's another example. I had to turn it sideways to make it fit. But if you just look at the hash marks, it's a big skinny island that contains a skinny pond, that contains an island that contains a pond, all the way down to the middle where there's a single island. And the output would look like that. So we got this outer A island that contains a B island, and so on. So we want to write a program to read in the one form and write out the other form. Now my assignment wasn't exactly like this. I don't remember the exact details, but the key to it was to identify the islands. Okay? So what we're going to use to do it is called a flood fill algorithm. So let me sketch the idea. So suppose this was the thing we were dealing with. We're going to scan the rows, the rows one at a time. So we'll look at that one first. And what we're looking for is some land. Now that's not land, that's not land, that's not land, that's not land. And then we find land. This is where the recursion comes in. This is just a loop so far. When you find the land you're looking for, what should we do? We should sort of change modes now. We're not going to, we're sort of done searching, we found some land. Yeah?
Find adjacent land?
We want to find all the adjacent land and basically flood it with A's.
Right.
You know, so if you think about if you imagine the hash marks are a little bit lower than the land, well, that's not the right analogy. We kind of want to flood the land, if you will. We want to flood it with A's. All right? And so when we find land, we flood all the adjacent land with A's. And then we keep searching. No, no, no. We find another one, so we stop what we're doing, flood it full of B's. We keep going. So that's land, but we've already dealt with it. We're looking for land that isn't marked yet. And that's as far as my demonstration goes, but we would keep going and hit the other two and label them with C's. Okay?
So from this, I would assume the 2 pieces that are just adjacent to each other are not part of the same island?
Right, so diagonal doesn't count as adjacent.
Okay.
Right. So you have to, adjacent is just vertical or horizontal. Okay? So that's that. Let's look at that. Let's look at some actual code. Now the other thing about this example is it uses 2-dimensional arrays. And 2-dimensional arrays turn out to be kind of useful for the assignment you're doing right now. So the array part would be useful for Connect 4. Not so much the recursive part this week. So let's go to recursiondemo.java here and take a look. No, recursion demo. Pondsandislands.java, that sounds better. Okay, so let's first look at the non-recursive parts. So here's the main method, and you can see what we do is we have a method called readMap. So it reads from a file, a map, and in fact here you can see what the maps look like. Here's map1.txt. It's just the example we saw. Here's map2.txt. It's the other one. So we got this stuff stored in a file. So we read it in, and it's returned, and it's stored in a variable called map. Now what type is this? That's a two-dimensional array of chars. So if you can think of it as having rows and columns, if you like. And the first parameter, the first index, if you want to index into it, you say map sub I sub j, and it'll give you, row I, column j, however you want to visualize it. So read map creates and returns a two-dimensional array. Write map displays it. Then we mark the islands on the map, and then we write the marked map out again. So if I run this, what you'll see is I'll take map 2, and there's the, it printed out the unmarked map, and then it printed out the marked map. So we'll quickly look at the code that does the reading and the writing. I'm most interested in the marking, though. All right, so here's the code that does the read map. This section of code isn't using two-dimensional arrays. All it's doing is it's using an open file dialog to get the file. It creates an empty array list, and then it reads one line at a time from the scanner and stores them in the list. So we end up with a list of all the lines in the file, which are supposed to be all the same length. So we don't do any, I'm not doing any error checking. Okay? So we got that array list read, and let's focus on this then. We create a new two-dimensional array of characters. And you have to give the size of the first dimension and the size of the second dimension. For this type, there are actually several ways to do two-dimensional arrays, but this is the simplest form of two-dimensional arrays, where all the rows are the same length. Okay? So why is the first dimension the number of lines? Yeah?
Isn't it because a 2D array is just an array of arrays?
Yeah, actually, he's right. A two-dimensional array is just an array of arrays.
So it would be the number of arrays that are in it, which would be the number of...
Right. But it's also, that is literally true how it happens internally. I would encourage you, for this example, where the rows and the arrays are all the same length, just to think of it as a two-dimensional rectangular array with some number of rows and some number of columns. So why does it make sense that the number of rows is lines.size? Yeah?
Is that would be the number of rows that are in the line?
Okay, so that would be the number of rows that need to be in the array. Okay? So each line from the file describes a row in the array. And then this would be the number of columns in each line. What am I doing there to get the number of columns out? Yeah?
You're taking out one of those lines and then figuring out how many items are in that.
Right. So I'm taking the list of lines that I read. I am getting the first line from it and getting its length. And I'm assuming all the lines are the same length, so I just picked the first one. So that'll give us a rectangular array, the way to think about it abstractly, of characters. Then I iterate through the lines, and for each one, for each line, I iterate through the characters. So each line is a string, and so I take the map, I'm on a particular row, I'm in a particular column, and I get the character out of the line and stick it into the array. So I'm just taking the characters that were in the file and sticking them in the array. Now, why would two-dimensional arrays be useful for Connect 4? You don't have to use them. My helper method does, so you make easier use of my helper method if you use two-dimensional arrays. You could use two-dimensional lists. You could have an array list that contains array lists. Same sort of idea. So where would you use it in Connect 4? Yeah?
You think of the Connect 4 board.
Right, to represent the board. You need to know what pieces are in each column. So you got some number of columns, and the columns have rows. You need to know what pieces are where. So anyway, that little method just creates an array and returns it. To write out a map, I used the special for loop. What's this outer for loop doing? What's it taking out of the map? So in this case, you need to think of the map as being an array of arrays, an array of rows. So what I'm doing is I'm just taking from the map one row at a time, and each row is an array of characters. So I'm pulling out a character array one at a time from the map. Then I'm iterating through the character array and pulling characters out, and I'm just printing the characters. And come to think of it, I can think of a simpler way to do this. Well, never mind. I was thinking that was a string. If that was a string, I could just print it out. But it's a character array. Okay. Now we get to where the action is. So I want to mark each island with a different letter. So I have a character that I'm using as my mark. And what's going on here? That's typical of how you iterate through a two-dimensional array. We have an outer loop that iterates through the rows. We have an inner loop that iterates through the columns. And I'll just tell you, I had to concentrate really hard to avoid writing row plus plus right there. I may have told you before, I make that mistake all the time. I increment the wrong variable in a nested loop. But so very typical for two-dimensional arrays, you have a for loop that iterates through the row indexes. You have another that iterates through the column indexes. And what we do is we attempt to flood the map at that row and column, so that particular square. So if that turns out to be land, the flood will do its thing and return true, and will increment mark. So next time mark will use a B instead of an A. And if it turns out not to be land, it'll just return false. So what this method is doing is the equivalent of what I was animating. Yellow, yellow, yellow. The yellow is moving along, and when it hit land, something happened. And then it moved along till it hit land again, and something happened, but this time with a B instead of an A. Okay? So we're just traipsing through the array, looking for things to work on. Yeah?
What do we have defined as land?
Land is the character hash mark. Water is a hyphen, just like in my demo. Those are the only two characters that are allowed in the input file. Okay, I meant not to show you this. Okay, so flood's job is we're saying here's a map, here's a row, and here's a column. So it says go to that point in the two-dimensional map, and if that's a hash mark, replace it and everything adjacent to it, every hash mark adjacent to it, and that's adjacent to the adjacencies, with this mark. So, and return true. And if it's not a hash, return false. So you can see right here, if the character stored at the particular row and column of the array is a hash mark, we return true. Otherwise, we return false. Okay? But what should we do before we return true? What's the first thing we should do? Yeah?
Well, we need to check if the current one is this, and then check the adjacent.
Yeah, well, we know the current one. If we get to right here, we know that the character at that location in the array is a hash mark. So that's land. So what do we do with it? Yeah?
We need to mark it.
We need to mark it. So how we do that, we just say, okay, let's convert that. Let's store the mark there. So that's just saying, okay, replace that hash mark with the mark. Now that just replaces one. There may be a whole bunch of ones that are adjacent. They may be to our north, they may be to our south, our east, to our west, we don't know. Now I can remember this assignment, and the assignment actually suggested trying to do some trick like walking along the perimeter of the island and identify the perimeter, which I don't know if they didn't know how to solve it themselves or if it was meant to be a red herring, but that's a really bad way to do it. It turns out all you got to do is that. Make 4 recursive calls to flood. There's the recursion. So let's break it down. What's happening here? Yeah?
This where is mark defined?
Mark is passed in as a parameter to flood from the method that called it. So it's the letter A or B or C or D or whatever was determined. Yeah?
This is flooding what's below.
Okay, so we're adding one to the row, notice. So it's trying to flood the square below and everything adjacent to it. Because as soon as we call it, let's say the square below is a hash, what's going to happen? Yeah? Right, so it'll mark that square, and then it will try to flood everything adjacent to it. Now what's going to happen when it tries to flood the thing above it? It will not be a hash anymore, it'll be a mark. And so it won't continue from there. So it turns out that if you try to flood everything above you, and everything below you, everything to your right, and everything to your left, it'll eventually find everything that's reachable and nothing more, and set them all to hashes. Yeah?
I think we can just examine the map, which is on the right of the current map and below the current map, because we checked the map one by one, so it's from the
Okay,
map.
so he's suggesting that I don't have to work that hard. So as I scan, I'm finding sort of the part of the island that's in the upper leftmost corner of the island, right? Because I'm scanning from above and scanning from left to right. So he's saying I don't really need to look up or left, because I would have hit those pieces already. I need to look down and right. And that sounds good, but let me do this. Let me do it over here so you get on the camera. Suppose that our map looks like this. So we got a bunch of this. Let's say we got a hash here. This is the first. Well, sorry about that. I'm going to put the hash here so I have more room.
Right to your right, the eraser.
All right, so that's the first one. So we know that there's not going to be something above it. What if you had this kind of situation? So the island, this is sort of the upper part of it, but it sort of turns around right here. If you refuse to look left or up, you won't find this chunk. But you're right. The very first time, there's no need to look left or up. But every other time, there is. Now, what would happen if I didn't mark until I had flooded? Something very subtle happens. Yeah?
It would, in the other calls that are looking in for trying to flood the other ones, it would call flood on the one like to the right, and then the one to the right would try to flood the ones to the left, and it's not already marked.
Okay. We would get to an infinite recursion again, I think. Because,
Repeat.
okay, so what he's saying is, if we don't mark, okay, when we marked before, when we try to flood the thing below us, and it in turn tries to flood the thing above it, namely where we started, it's been marked, and so it ends the recursion right there. But if we don't mark until everything is done, nothing ever gets marked. It just bounces around. So let's try it and see. That's my intuition anyway. I've been wrong about these before, so. Yeah, so we got an infinite recursion there. So that's pretty subtle, but important. Okay, now, the kind of recursion that we saw first with the binary trees, that's called structural recursion. Because the structure of the program, the recursive structure of the program, is just a reflection of the recursive organization of the data structure being consumed. This situation, we're not working with a recursive data structure. We're working with a 2D array. Recursion is still useful. This is called ad hoc recursion. And ad hoc recursion is harder to understand, harder to deal with. In particular, you see the subtle effect when we just change the order of a couple of statements. You may not have thought that would cause infinite recursion. On your assignment, you'll have one of each. A structure recursion, which I mentioned with the mobiles, and also a flood fill application. Now, have any of you ever played a game on a computer that uses a flood fill algorithm? And if you haven't, probably your parents have. Yeah. Minesweeper. Right? So in Minesweeper, I don't know, it's not, have any of you ever played Minesweeper before? Okay, it's still a thing. So when you click on a blank square, what happens? You basically got a two-dimensional map, and when you click on a blank square, it shows you all the blank squares connected to it. So that's a flood fill. So we're going to give you a version of the game that Stefan wrote, but we'll take out some stuff you got to put back in, and one of them will be this, we'll require flood fill. Yeah?
So like the parameters inside the flood method, I guess, just kind of confusing. Like, what happens when you do row plus 1 and row minus 1 and then column plus 1?
Okay, so draw it here. If you think of a two-dimensional array as a grid, of rows and columns. So suppose we call flood and we give a row of 2 and a column of 1. So which of these cells are we talking about? Remember, it's zero-based. So what are we asking it to flood? Okay, row 2, so 0, 1, 2. Column 1, 0, 1. So we're talking about this square right here. So the index of that square is 2, 1. So if we were doing an array, it would be map sub 2 sub 1. It would be the character stored right there. How would you compute the coordinates of that thing right there? Same column, right? The row is one smaller. So if you're somewhere in the array and you want to go up, you subtract 1 from the row and leave the column the same. What if you want to go down? Add 1 to the row, leave the column the same. Left and right, you keep the row the same, but you either subtract or add to the column. If you look at the helper method I gave you for Connect 4, you'll see that sort of thing going on. It's got to find 4 things in a row, so it's doing those sorts of calculations. Other questions? I was just thinking, when we were walking over here, Stefan was talking about taking that flooding phase where it finds all the blank squares and making it run slowly so you could see the wave propagate. And that's a way of visualizing a flood fill algorithm. You can see what gets filled first and what gets filled later. So we'll try to make that work. Okay? Well, let's take a break, and I got one more example of recursion for you. Okay, let's get started again. So I had some questions. So I changed, this is map 3, so I put a little leftward hook in it here. Actually, that one already had a leftward hook. So let's, if I take out, if I never look above, or no, if I never look above, and I never look left, let's see what happens when we solve map 3. Okay, so what happened there? We look at the solution. What went wrong since we refused to ever look left? Yeah?
I made a file with a new piece of land moving out, but directly to the left of that, maple trees looking line.
Right. So what he's saying is, okay, it found the first island okay, but since it would never look to the left, it didn't find these two pieces in the same island, so it get marked as separate islands. So it finds them and it marks them, but they're not marked correctly. And the same thing happened with the other, the H and D one down there. So yeah, it's important to look in all 4 directions, although it may seem redundant. It's also important to mark before you make the recursive calls, because that way, see, you always got to be able to argue that this is going to terminate. So what's the argument that this will terminate? What is getting smaller with each recursive call? Or with each 4? Yeah? Right. So the number of hash marks on the island you're marking gets smaller. So you make a mark, you make 4 recursive calls. None of those will make any more recursive calls until they mark something. So that's getting smaller each time, so you can't have the infinite recursion. Yeah?
So does flood just remove a hash mark one at a time?
Yeah. Flood removes 1 hash mark at the current spot, and then recursively tries to flood everything above it, below it, to its sides. And then the other things get marked because of that recursion. And the beauty of it is you don't have to know the topography of the island. Is it, is it compact, square? Is it all spread out? It just finds everything that's adjacent and marks it. Yes?
For the viewers on the camera, can you show quickly what it does when you put the map below the floods?
They didn't see that?
No.
So put this below?
Yeah.
Okay, so if we mark, do the recursion and then mark, what we found is we get an infinite recursion. Because it just keeps recursing and never gets around to marking. Because the recursions never return. Yeah?
Another question after what I asked about mark earlier. How does it know, I don't see where, how does it know whether to make the mark A, B, C, etc.?
It's this parameter right there.
Yeah, but where is it specified that mark equals A?
Right there.
Okay, there it is. And what method is that in?
Well, this is the one that's systematically looking at every row and column, every location in the array, and it attempts to flood it. If it turns out that the flood was successful, if there was an island to flood, we increment mark. So when you add 1 to a character, you just get the next character, which is B.
Here it is. I see.
Yeah. Now, if there are more than 26 islands, what's going to happen after Z? Yeah? Well, we're using capital letters now. But the thing after Z is, I don't know. Let's find out. So we'll mark starting with Z and see where it goes from there.
Did you?
Yeah, I fixed it back. So it looks like left square bracket is first, and then backslash, and then close square bracket, and then caret. Who knew? And then very shortly after that, the lowercase letters begin. So, kind of weird. But yeah?
So there
Well, okay, so that is a worry. If hash mark comes after Z, yes, that would be a problem. It may come before, though. Yeah? No, sure. Well, we're talking Unicode here. So Unicode is 32 is 4 bytes. No, 2 bytes. 16-bit. So, you know, there's, what, 16,000, or I forget the exact number. But anyway, there's thousands and thousands of Unicode characters. But you start seeing weird ones up there. You start seeing, well, the attempt to add the Klingon alphabet to Unicode failed. But lots of real alphabets that are in there.
Ew, but when did they add that there?
What?
When did they add the Klingon alphabet?
They didn't add it. It was a proposal to add Klingon to the to Unicode.
But you'll get stuff like, I don't know, like Arabic letters?
Sure, you get Arabic, or you get Cyrillic,
Yeah, the Greek letters.
Greek letters, math symbols, everything. Okay. I promised you one more example, so here we go. I've got to find it. Oh, I had it. Wait.
Yeah.
Okay. This is a recursive data structure that you use all the time, namely the file system on your computer. So on your computer, you have your file system is organized into folders and documents. So you might have a folder called Docs that contains 3 folders. And maybe the CS1 folder contains a P1 folder and a document called a.java. Maybe the CS22 folder is empty. The CS333 folder contains 3 folders. This one contains 2 docs. This one contains nothing. This one contains 1 document. So that's your file system. Arbitrarily large, that's what it looks like. Now you got to be careful, because sometimes in file systems you can have links that go to other places in the file system, and you no longer have this nice tree. So when you use the program I'm about to show you, it has to be on a nice, well-behaved chunk of your file system. Don't try to run these things on the entire root of your file system. You're almost certain to find an anomaly somewhere. Now, what kind of tree is this? Is this a binary tree? No, this is not like the pedigree tree. It's like the descendant tree we talked about. The number of branches out of a folder just depends. Okay. Nevertheless, I claim there are only 2 kinds of file systems. So look at my symbols here. I've got this thing here is a folder symbol. This is a document. And I'm going to let triangle to stand for either one. Either a folder or a document, which is what Java calls a file, turns out, with a capital F. So to Java, a file could be a folder, or a file could be a document. So what would be the 2 kinds of documents? The 2 kinds of file systems. What's the simplest file system you could think of? Yeah?
File system that's empty.
Well, a file system that's empty, we're actually not going to have that. I'm not going to allow an empty file system. So what would be the next simplest thing? Yeah? Just a document all by itself. So a document all by itself is one kind of thing. And what's the other kind of file system? Yeah? A folder that contains simpler file systems. So rather than think of, when you're thinking about a file system, rather than thinking about it like that, which is kind of confusing, just think about it like that. There are only 2 kinds. It's either a document or it's a folder that contains 0 or more simpler file systems. And those triangles could be documents, they could be other folders. Doesn't matter. If you think about it this way, then it becomes a lot easier to write programs. Let's imagine writing one. Suppose I ask you to write a program to count the number of documents in a file system. So given a file system, tell me how many documents there are in it. So what would be the answer for this kind of file system? If the file system was just a single document, what would the answer be? One document. What would it be for this case? How would you calculate the answer for that case? Okay, you would calculate the number of documents in this one, the number of documents in that one, the number of documents in that one, and add them up. Now, how would you calculate the number of documents in this file system? You make a recursive call. So this is the shape of methods that consume file systems, or as Java calls them, files. This can get confusing. We're calling them documents and folders. Collectively, Java calls them file with a capital F. So if we're trying to write a method here that takes a file as a parameter, okay, and this is also confusing. You would think that if you asked, is F a file, it would always be true, right? Because it's called a file. But it turns out, is file tells you, is it a document? Okay? So I wish that was is document. But anyway, it says if F is a document, I'll read it that way, you do something without recursion. Otherwise, you have to iterate through all of the file systems that are contained by F and make a recursive call on each of them and then combine them somehow. So that's the recipe for a method that consumes a file system. Why does it involve a loop, whereas with the Pedigree Tree there was no loop? Yes?
Because you don't know exactly how many documents or file folders are in a certain...
Right. We don't know. In the other case, we always knew there were exactly 2 pedigree trees. In this case, we don't, there's no set number. So you have to have a loop that will deal with them all. But it's easy to do that. F.getFiles returns all the file systems that are under a folder. And then we just make a recursive call on each of them. Getting any questions on your phone there?
Yes, by the way.
How about that? Too complicated.
It's a very complicated question.
Yeah. I think we'd better...
You want to read?
I think that's... Maybe we'll answer it after class. Got to ask simple questions.
We're talking about installing Windows 10 on a system.
No questions about installing Windows 10. Not during class. Okay. Let's see this in use. So this is called filesystemdemo.java. And you can see what I'm doing is I'm running, I've got 3 methods, count files, largest file size, longest file name, and I'm calling it with a file. This is my workspace. So you see my workspace on the left there. I'll be testing them on the workspace. And hopefully it's not too big. I didn't try it out for a class. So let's see. Should be able to write 1 anyway. Okay, I want to count how many. This says count files. I've changed my notation here, so let me change this. I'm going to call it count documents because that's the word we've been using. I'm going to count the number of documents in the file system F. So what was our idea? What was our skeleton? What's the first possibility? Okay, so it may be that F is just a document all by itself. And there isn't an is document, but there is an is file, which means is document. Okay. And we decided, okay, if it's just a document all by itself, the answer's got to be 1. Right? There's a document. It doesn't contain anything else. Great. And then there was one other possibility that actually F is a folder. So what we need to do is make a recursive call to count documents. So somehow we got to call to count documents on all the things that are contained by that folder F. So we need a loop. Now, what was the name of the method? Not isFile. Hold on. Get files.
I don't see that as
Huh. Well, my slide is wrong. It returns an array of files. What's it called? List files. What a stupid name. So list files returns an array of all the files that are contained by F. So for each one, I got to do something. So what kind of loop am I writing here? I've got a bunch of file systems now called, each time through the loop would be a new file system G. I've got to count the documents in it, and then I've got to add them all up. What kind of loop is that? No, I mean accumulation, other thing, yeah. What I said, accumulation. This is an accumulation loop. You're just adding a bunch of stuff up. So let's do that. There's our count. There's our accumulation variable. So it's going to be, we're going to take total, into it we're going to add the number of documents contained in G. And we've got to return total. So there's that little piece of code that could traverse your entire file system and count how many documents there are. That's just the power of recursion here. And here's the recursion. For the file system, the recursion is going to appear inside of a loop. For every smaller file system, we have to make a recursive call. Think it'll work? I have my doubts because the file system is so big, I'm afraid there's going to be some freak occurrence that kills it, but we'll try. So 2,249 files in my workspace. Yeah?
Well, if we're writing this on our own computer, how can we modify it so it'll work for our computer?
Okay, if you're running on your computer, you need to modify it. Up here's where I'm making the call. So you just want to put the path name to some folder on your computer. And how you write it depends on whether you're using Windows or Linux or whatever, Mac OS. Okay? So we'll look at another example, but before we do that, let's look at this one. This is about as simple as they get. You got the base case, you got the recursive case. The number of recursive calls made depends on the number of file systems that the folder contains. And, I realize it's a little mind-boggling because there's a loop that contains a recursive call. So the recursive calls are being made over and over. That's enough to traverse deep. Yeah?
What is the variable G?
Okay. So that there is an array of all the files contained in the folder F. And this is just a for each loop. Each time through the loop, G takes on the value of one of those elements in the array. So we're just stepping through the files contained in the folder. Yeah?
If you assign total the value of itself plus count documents, do you need that second instance of total if you just assign count documents?
Well, if
plus equals.
You mean that?
Yeah.
Okay, what will I get if I do that? Let's run it and see. It gave me 1 back. The problem is you're only counting, in the end, you're only returning the number of documents that were contained in the last folder in the last, actually probably, there are a bunch of folders in my file system, but I'm not paying attention to any but the last. Right? I call count documents on the first one, I assign to total. Then the loop goes again, I call count documents on the second one, and I change total. I've lost how many documents are in the first version of G. So I definitely need to do the adding like that. Yes?
Out of curiosity, is it possible to get in a situation where through normal looping and recursion, you get a stack overflow even though that wasn't infinite recursion?
Okay, so he's asking, is it possible to get a stack overflow even if the recursion isn't infinite, it's just really deep? And yes, it's possible. Now, to do that, you have to go tens of thousands of level deep in recursion. Now, that's probably not going to happen on my file system because I have not created a folder system that extends 10,000 deep, let alone 60,000 deep or whatever it would take. But if I calculated if I took my recursive factorial program and just computed fact of 1,000,000, it would definitely blow the stack. Now when that happens, you can configure Java to allocate more space to the stack. You can play that game. But then I can just compute fact of something even bigger. It's not all that common. Other questions? We'll do one more example, but I want to make sure I've got all I can out of this one. Okay, this says if F is a document, returns its size. Otherwise, returns the size of the largest document. That's how I should read it. I need to change this after class. The fundamental problem is that the terminology used for folders, what you call a folder in Windows is in Linux is a directory. I want to find the size of the largest document in the file system. Okay? So let's take our starting point here. And I want you to think for a minute. If F happens to be a document, what should we return there? I'll give you 15 seconds. Because the answer is pretty straightforward. What should we return if our parameter happens to be a document? And we're asking, what's the largest document in this file system? Yes?
The size of the document.
The size of the document. So that's F dot
Wait a second.
length. Returns the length of the file. Yes?
Shouldn't we be doing that for largest file size? Because here on largest document, I thought we should be returning the name, not the size, because that's for the upper method.
Okay. That's a reasonable objection. So we'll call it size of largest document.
Well, then what's largest file size for?
Largest file size.
Longest.
Just right above us.
That's longest file name.
Well, that's...
Let's just concentrate on this one here, size of largest document. So if F is a document, we return its length. Now, as an aside, length returns a long. Why do you suppose length returns a long instead of an int? Yeah?
Is it in bytes?
It's measured in bytes.
So it would probably be really big for large
Right.
files.
So the largest positive int is 2 billion and change. So if you can have more than, if you have much more than 2 billion bytes, 2 gigabytes in your file, it wouldn't be, the size couldn't be represented with an integer. So longs are used. Okay, so if f is a document, we return its length. If f is not a document, we've got to go find the largest one. Okay? Well, how are we going to do that? What kind of loop are we talking about now? We're looking for the largest document somewhere under us in this tree. Yeah? Well, not a searching. Optimization. We're looking for the largest, right? So let's say largest size so far. So initially we'll set to 0. And how should we update it inside the loop?
If g.length is greater than largest size so far.
Okay, so if g's length, oh, we need a recursive call in here, right? We recursively got to find out the size of the largest document in the file system G. That didn't work. Okay, so if the size of the largest document is greater than largest size so far, so if we examine the file system G and we find out that it contains a document that's larger than the largest one we've seen so far, what do? What do you always do in an optimization loop? Yeah? Right, that's the new largest. Should that be what? Yes, thank you for pointing that out. This should be a long, definitely. And then we return largest size so far. Okay, so let's review. We're dealing with a folder, so we have this optimization variable here. We look at everything the folder contains. We figure out what the size of the largest document contained in that thing is. If it's bigger than the largest one we've seen so far, we have a new winner. When we're all done, we return that. Now, there's one really bad thing about this method. But let's see what happens when I run it. So it counted, okay, and it took a while to come up with the largest. Can you think of a way to speed it up? What's the problem here? What's the slow operation in this method? Yeah?
So you need to call the size of the largest document twice. Once to figure out if it's bigger, and once to actually assign it if it is bigger.
Right. We're calling that method there, and then we're calling it again here. And if it's a large file system, we're sort of applying the same method twice to the same thing. The answer is not going to change. So it's more efficient to first calculate the size and then just use that variable down here instead of calling the same method twice. That'll make a difference in the running time. It could be the difference in it finishing or not finishing. So if we run it now, let's see how fast it is. So it found it right away then. So I somewhere in here have a 64 megabit document. That's my biggest one. Yeah?
How is it determined the size of the document? What's that being measured?
The size of the document is just the number of bytes that the document has. That's something the operating system
might
does.
give me one.
Hmm?
Very strange that mine would give me one.
Well, just be sure that when you're using the length method to get the size of it.
Oh.
Okay? So I realize that with this example here, I'm kind of pushing, you know, I just introduced you to recursion on Tuesday, and now we're looking at recursions inside of loops. So, I'm asking a lot of you to stretch your mind around this. But my bigger purpose is to show you the power of recursion. Even if you don't understand what's going on here, just focus on the fact that you can have an arbitrarily large file system, and this relatively short amount of code is sufficient to consume the whole thing. I mean, I guess I could dare to try this. Let's see how many documents are on my entire computer. And I warn you that there can be these loops because of links, but we'll see. Yeah. Oh.
It's because if you have a blank folder.
Well, if I have a blank folder.
If you have a blank folder somewhere, you'll get that exception.
Okay.
That's what I just discovered.
Okay. So I need another test in here. These are not. This is one of those conditions coming up where she's saying an empty folder is causing that problem. I'll check it out before I post the code. So we want to see how long it takes to run. Okay, let's end there.